So what if we conducted a different random sample of 1,019 Americans aged 18 years or older? Would we get the same sample proportion who believe the amount of income tax they pay is fair? Probably not, because statistics such as p-hat vary from sample to sample. So a different random sample of adult Americans might result in a different point estimate of the population proportion, such as p-hat equals 0.593. If the method used to select the adult Americans was done appropriately, both point estimates would be good guesses of the population proportion. Due to variability in the sample proportion, we report a range, or interval of values, including a measure of the likelihood that the interval includes the unknown population proportion. So this paragraph was just, or 2 paragraphs, was explaining why we report a range instead of just a number. So again, with estimation, we report a range and a confidence level. So how confident are we that it falls within that range? And that's what we're working on right now. So let's review the sampling distribution of the sample proportion. So I'd like you to try and fill these in from what you've learned in Chapter 8. So when is the shape going to be approximately normal for a sample proportion? And you can refer to your overview sheet. We're on sample proportion, so it's normal when NP times 1 minus P is greater than or equal to 10. Here's independence, here's your mean and standard deviation. So we can just basically copy those over. So N times P times 1 minus P needs to be greater than or equal to 10 to be approximately normal. And we can just include the independence in this one. So your sample has to be less than or equal to 5% of your population. Your mean is mu sub p hat equaling p. Standard deviation is sigma sub p hat equaling the square root of p times 1 minus p all over n. So let's look at this over here. So we're going to be looking at 95%. Okay, so we're going to want to be 95% confident, and then if we're 95% confident, it's going to fall within this range. If you recall the empirical rule, we had 1 standard deviation from the mean was 68%, and then 2 standard deviation was 95%. This was roughly, right? So if you want exact to get 95% under the curve in the middle, it'd be 1.96. So very close to the 2 standard deviations out from the mean. But 1.96 is just exact. So you can see here, 95% is in the middle, leaving us with 2.5% each tail, equaling 100% under the curve. So the 95% confidence interval does not include the population proportion, then more than how many standard errors? It'd be 1.96, because if it was outside 1.96 standard errors or standard deviations, it's not included in your 95% confidence interval. So let's look at what percent of sample proportions results in a 95% confidence interval that includes the population proportion. So we have 95%. What proportion do we think would cover? That would be 0.95. So then what population proportion is not included? So what's on the outside in it as a proportion? 0.05. Or if they're looking for percents, you can say 95%, 5%. All right, let's move on to the confidence interval. This is for an unknown parameter. It consists of an interval of numbers based on a point estimate. We're going to use number 9 on our calculator sheet. And let's define the level of confidence. This is the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted by 1 minus alpha times 100%. And I'll get into that a little bit later. So let's look at the key ideas regarding confidence intervals. First, a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted 1 minus alpha times 100%. And whether a confidence interval contains a population parameter, so here's a population parameter, depends solely on the value of the sample statistic. So again, here's a population parameter. Any sample statistic that is in the tails of the sampling distribution will result in a confidence interval that does not include the population parameter. See the figure. Notice that p hat 1, so here's p hat 1, results in a confidence interval that includes the population proportion. So here's the confidence interval from this p hat 1. And it's including this population. So then look at p hat sub 2. Okay, here's that confidence interval. Notice it does not contain the population proportion because p hat sub 2 is in the tails of the distribution.